Hello and welcome to this edition of a tutorial on R where you're going to use R and we're going to calculate power and sample size in R. Now this is a very important part of our lecture series because in here we are going to focus on using R for really putting together a study. And one of the things that you need to do when you start to put together a good study is you have to plan. So as we have mentioned in one of the previous lectures, that in order to put together a study, the first and probably the most important thing that you do is you start with a theory, and from the theory you start developing your hypothesis, and those hypotheses will then drive the process of your that hypothesis generation process will then drive the rest of your research. So you develop your hypothesis and then put your hypothesis to a number of questions, and then the questions will drive the data that you will collect, and then after you collect the data, what you will need to do is you will then analyze them and do the rest of it. So you can see pretty much that the most important factor that will drive your data analysis and your entire research process is a careful planning of your research. And the most important element of a careful planning of your research is the process of ascertaining how many people you will take in your studies, and what would be the power of the study. In this lecture, in this tutorial, this is something that we are going to touch to some extent. So grab a piece of paper and a pencil, and we'll start working on a few tables and things like that to make sense of this. And then I'll show you that using R, you can quite easily and very intuitively, you can calculate the sample size of almost any study that you want to do, as long as you know what you're doing. And here there is a very nice package which is going to be a real friend in getting those things done. But you also understand that you can actually write your own packages and your own functions from articles, from tables, from some sort of an information that you may come across while surfing the web, and some of the other means that will enable you to actually then program R in ways in which you can extend R in order to find out that information. So that is very important as far as your working with R is concerned. So in this tutorial, this is what we are going to do, and this is called calculation of the power and sample size in R. So next, let's give me a little bit of my introduction as to who I am and what is the context of this series of lectures, and that will help you to make sense of what all this is about, and then we'll go underway. As you know, my name is Arindam Basu. I'm from the University of Canterbury. The University of Canterbury is a publicly funded university located at the city of Christchurch in New Zealand. And this is a series of things about R programming. So that's this. And one of the things that we'll do is let's take a look at the learning objective first, and then we'll take a look at our things that we're going to, the overall objectives of this tutorial, and see how it goes. Okay. The first thing about the learning objectives for this series of tutorials is this, that we're going to cover concepts as opposed to show you that I'm going to take a data set and then walk you through. That's something that I have done previously, but this time we're going to deal with mostly concepts or kind of simple models or kind of things and ghosts in our minds. So we'll learn a few things about the testing theory, about the hypothesis generation, and we will revisit the 2 by 2 table that we had put up previously in order to explore what is meant by hypothesis generation. We'll also revisit the concept of what is known as power, and I say revisit because we have already come across this in one of our earlier tutorials, so I'm just going to repeat that information over again to make sense. And we are not going to do so much as sampling here, but you understand that the basis of sample size and power calculation is a good understanding of the fact that you are not going to get a census, you're going to get a sample of individuals. And then we shall finally summarize some of these things. In the process, I'm going to show you a few R codes. So before I go ahead much further, I would like to talk about some of the requirements of sample size and power calculation. So which is going to be something that we're going to talk about in the next slide. And then I'm going to show you that you can calculate sample size and you can calculate power very easily using a package, and that package is called PWR, and we'll see how it works. It is a very simple package. That package is called PWR, and if you have not installed PWR yet, then please install it now, because we will be using this power language and the library quite a lot, and so we'll see how these things work. And when you do that, it will ask that you will have to install the dependencies and say yes that you want to install the dependencies, because you will need the full power of the PWR package in order to get some things done. Now, before I go ahead and start showing you some of these things, which you will later on see are actually very simple as it gets, because we are going to use the Cohen's framework of effect size estimates. You will need essentially three things for your sample size and power calculation. The first and probably the most important thing in order to calculate your sample size and power is a notion of the effect size. The word effect size, or the phrase effect size, basically means that if you are conducting a study in which you would like to compare the effects of two interventions, or if you are conducting a study, or if you are engaged in a research in which you would like to study the difference in the outcome of two exposures, then the magnitude of that difference is very important. The magnitude of that difference can be expressed both in terms of the difference of the average responses, or in other words, what is the average value of the outcome in each of the comparable groups that you want to study. I'll give you an example. For example, let us say that you are interested to study a group of diabetics, and you have made a modification in a particular drug that is very, very good for anti-diabetic properties. What you do is this, that you get, say for example, 100 diabetic patients. In one you give them the new drug, and the other you give the traditional treatment. After about 3 months of therapy, you would like to test the outcomes. A very popular outcome in diabetes research, or probably the most standardized outcome in diabetes research, is a metric known as glycosylated hemoglobin, and it is given in the form of a percentage. So what you want to do is this, that after taking some baseline measurements, you give each of these groups your drugs, and then you want to follow them up. So in the treatment group, you make a measurement of your glycosylated hemoglobin. In the comparison group, you also take a measurement of the glycosylated hemoglobin, and then you take a measurement. The difference is very, very important for you. But what is very important here is the outcome difference is an entity or a measurement that will determine the sample size that you will have to start when you conduct that study, because you're going to take samples. And so your sample size will be dependent on the effect estimate that you're going to expect when you conduct a study. And that effect estimate is the estimate of the difference in the magnitude of the effect of each of these, either intervention or the control condition. This is one way of studying the effect size. Another way of studying the effect size is, and the example that we have just talked about is what is known as an absolute effect. But there is another way in which you can study effect size, and that effect size study is by using a relative effect estimate. Say, for example, you are interested in conducting a randomized control trial. So on the same group of participants, but this time you are taking an active drug and a placebo, or maybe the traditional medicine. So again, let's say you take about, I don't know how many number of people that you're going to take. That's something that we're going to decide. But what you do is this, that then on these groups of people, on one set of people who are randomly selected, you ask them to take the new medicine, the new drug, the ND, and the other ones you give them the traditional drug. And then instead of actually measuring their HbA1c levels anymore, you're saying how many of them at the end of 6 months could achieve a very good control in each group. And the proportion of people who achieved very good control in both the drug group and the control group are the numbers that you estimate. And then you make a comparison by taking a ratio of those numbers. This approach is known as estimation of the relative risk, or the relative effect estimate, or the risk ratio estimate. So what proportion of patients got better control in the new drug or the intervention group, what proportions of patients have got better control in the control group, and you take a ratio of them. That is known as a relative risk estimate. If the relative risk estimate is less than 1, then you know that your new drug was protective and therefore effective. If it is more than 1, then you know that it was probably not very effective in doing this, or the other way around. In other words, if you find that there were more people who benefited from your drug than the placebo, then you know that your drug was useful. Sometimes it's the other way around when you start taking a look at the risks that have, or the adverse effects that you want to study. Depends on your context. So effect size is very important. The second thing, which is very important and which we will be studying in the next set of slide deck, is the significance or the statistical significance that you are interested to find out. And this is somewhat related to the power of your study. So based on these 3 things, that is the effect size, the statistical significance that you want to uncover, and the power of your study, you will then calculate either the sample size or the power. And as I already said before, I recommend that you use the power package, the PWR package. If you have not already installed the PWR package, install it now. Once more, we are going to give you a little bit of a theory to start with. The theory is this, that in your endeavor to prove your hypothesis or disprove your hypothesis or test your hypothesis, in your research, you start with a theory. The theory is your thesis, and based on the thesis, you will then put together what is known as hypothesis. And hypotheses are, and you will settle on what is known as a null hypothesis. And there is a philosophical transaction to this. However, sufficient here to say that your null hypothesis is something in which you leave the option of an equality. So let us again invoke our old example of the diabetes medication to get started. Imagine that you are conducting a study of diabetic medications where you have developed a medication of a new drug which you think is going to be very effective amongst your patients who have got diabetes. You do not know how many people you're going to study, but you would like to find out, and this is the beginning of your research. So what you are trying to do is to set up or establish two hypotheses. First is the alternative hypothesis, which says that your new drug is going to be better than the old drug. So in terms of the number of people who will become, who will have better control of their diabetes or will have better control of diabetes using your HbA1c profile, you will find that those who received the new drug are going to perform better than those who received the traditional medicine. This is your alternative hypothesis. This is something that you want to challenge. In contrast, you will have to deal with what is known as a null hypothesis. And a null hypothesis states that your old drug is better than, or your old drug is either better or the traditional medicine is as good as the one that you are proposing. So that is known as a null hypothesis. So there are two things that you are contending with. One is the alternative hypothesis. The other is a null hypothesis. Let us think about this for a minute. That on the one hand, you have got the null hypothesis, which is what you're going to refute, challenge, and will work on. Now, when we say that we are going to focus our research essentially on the null hypothesis, so there are a couple of possibilities. One is this, that your null hypothesis is actually the correct thing to do. So, irrespective of whatever you find as a result of your study, your null hypothesis is the correct thing. Or the null hypothesis has to be rejected. So in other words, the null hypothesis cannot be rejected, or the null hypothesis will have to be rejected. Then you go out and you collect data. When you collect data, you find that under the tenets of the null hypothesis, the effects of your old medicine should be as good as your new medicine. But you find that your new medicine has given you better results than your old medicine, which means that under this condition then, you are about to refute or reject the null hypothesis. So, given this situation, there are four possibilities that you have to contend with. The first possibility is depicted in the top left cell, where we say that the null is actually correct, but you have rejected the null hypothesis, which means that you have committed an error. And this error is known as type 1 error or alpha error. There is another way in which you can commit an error, and that is, you have conducted a study, or you will be conducting a study, but as a result of this study, you see that the number of people who got better was roughly almost identically or very similarly equal, or the extent of improvement that you expected with your new drug is as good as with your old drug. So you could say that I cannot reject the null. However, in reality, you should have rejected the null because the null was not correct. So then you have made a mistake. One of the critical problems in the philosophy of science is this, that you are proposing something new. So you have got a medicine that you're proposing is going to work, but that medicine is pitted against another argument that both medicines are very similar. So which means that you are going to commit an error. What is the probability of that error? For historical reasons, it turns out that that probability of error is around 5%. So your alpha error is put at around 5%. Pitted against this is also another situation that you're going to commit another mistake. That is, you say that you fail to reject your null, whereas the null should have been rejected, which is type 2 error. And typically, this is put at around 10 to 20%, which then means that that situation where you have successfully rejected the null basically tells you that your study is that much powerful. So it's called the power of your study. Therefore, you set the power of your study to about 0.8 or 0.9, which is the 80% or 90% of your of whatever it is. Okay, so you set your power to be 80% or 90%. This is the theory with which we start. So we have now covered three things. The first thing that we have covered is that you must be mindful of the effect size of your research. The second thing that we have successfully covered is you should know what is the level of your significance. And the third thing that we have covered is that you should know what is the power of your study. The effect size is a very important thing that we must think about. The higher your effect size, the smaller will be your requirement or demand on the number of people that you will need to take in order to complete the study successfully. The smaller or the finer grain of the difference that you want to estimate, the more number of people you will have to take in your study. The alpha error is also very important. The finer your alpha error, in other words, the more certain that you're only going to commit something like 1% or less than 1% of your error, the more number of people you will have to take. The beta error likewise is also something like that. So if you want to reduce your beta error to something like 10% or 5%, you will have to take that many more number of people in order to do your work. These are tricky things. If you do not really understand, I'll leave that to you for some exercises to see for yourself once you start using the PWR package. So let's go ahead and start doing it. I'm going to show you two things using the PWR package. If you have not already installed the PWR package, then I urge you that you install the PWR package by using the function called install.packages and then give the name of the package, which is PWR, and type the word dip, that is DEP, and set it to true. So that way it is going to download all the important dependency packages, install them iteratively, and then will install the PWR package for you. And then you call the PWR package by using the command library within parentheses PWR. You can use a quote mark or you do not have to use a quote mark. It does not matter. And then what we're going to do is we're going to test a, say for example, a sample size for two-group t-test, two-sided t-tests. Okay? And we would set the difference, which is the effect size, as small. And I leave it to you to run an exercise to have the effect size as medium or moderate at 0.5 or large at 0.8 or 0.8 or more. See what it is like. And I've given you a formula for this. And the sample size estimate is given in the form of a formula, and a function is called PWR, which is the name of the package, then a dot, then a t-test, and then you will have to specify these three things. First, your effect size. If you want a small effect, that is a very fine-grained effect difference, you will have to put something like 0.2, and I would encourage you to read the book by Cohen and Cohen for sample size calculation in order to understand more about these things. You put your alpha error level or significance level at 0.05, and you put your power at 0.80. Now, obviously, you understand that you can have a number of different ways in which you can manipulate these numbers to see that, so that all the three variables will vary quite a lot. And then you let it run. When you do that, you will see that it's going to put out the n, or the sample size for the studies. Typically, if you type something like floor of n, it'll give you it'll round it down, so you can get something like 393 in each arm. Why is it so high? Because now you have decided to use a very low difference that you want to detect, 0.2, and you've kept it like 0.80 and 0.05, reasonable and quite conventional in terms of what is allowed. You could increase the effect size to something like 0.5, and you can see by how much the n value is going to come down. Okay, we'll use the same thing, that is using we'll keep the same things, except in this case what we're going to do is we say, for example, we do not have the wherewithals to take like 390 people in each arm of our study to make sense. Let's say, what happens if we have got only about say 200 people with whom we can work? So what we will do then is we will calculate the power of our study. Okay, so instead of calculating the sample size, we're going to calculate the power of our study. Take a look at this. And as I said, and this is a situation where you could take you're going to calculate, rather than the number of people you're going to take, you now are constrained by 200 people. So the power of the study is going to come down, right? And see what the power of the study is only about 50%. It's probably not going to be acceptable if your effect size, you still keep it at 0.2. But you can vary the effect size estimate, and then you can go back and run and rerun these routines, and it'll come back and give you the power that you will need for your work. Okay. This was a situation, and this was a set of algorithms that was put into place because we wanted to use an effect difference of an absolute effect, of magnitude of effect. But sometimes it is not the magnitude of effect that is important for us. Rather, it is the ratio of the effects that are very important for us. The ratio. In other words, we talked about the relative risk estimate that we want to do for our randomized control trial. And there can be other ways, like odds ratio or relative risk in a cohort study and things like that. So ratio is very, very important. So what happens when we have got the ratio that are very, very important for us? So let's see something else, the proportions of studies. And here, once again, you do the same thing, but this time instead of, so the code changes slightly. So instead of a t-test, you say that I'm going to use two proportions. Okay? Instead of comparing means, I am now going to compare the proportions of the two things. And usually these are two things that most people will work with. So you say power with 2p.test. You could have more than two proportions, but between pairs, you're going to make a comparison. This time, instead of putting it at a very fine level of difference, the Cohen's d, as it is known as, we have decided to put the Cohen's d, which is represented here in the form of an h. The letter h is equal to 0.5, which gives you a moderate effect size. And that gives you with a significance level of 0.05 and a power of 0.80, we see that we can get about roughly 63 people for a sample size. that 63 people would be enough for us to give that the difference in each arm of our comparison. So let's say instead of 63 people, we were lucky enough to get like 70 people. And then we plug in the same things to calculate our power. And here you can see that the power here is around 0.84. It is a two-sided alternative things. We could actually pare it down to one-sided, and then the number would increase a little bit. So this brings us to the end of this tutorial, where we learned how to calculate sample sizes and power for studies. We learned the basics of hypothesis tests. We knew that if we could use a package called PWR, we could do a number of different things. And hopefully you have picked up a few important tricks and things that you can do. So I again urge you to play with the R scripts and be well on your way. Thank you very much for paying attention.